because I have been assigned the task of discussing the coevolution of atmospheric and oceanic chemistry. Of course, that's a really broad topic. I think that there are several directions that I could have taken with this talk. But today my strategy will be to focus on the histories of atmospheric oxygen and methane on Earth and their relationship to the cycling of oxygen and methane in Earth's ocean. I'm going to do that in part because those are my favorite two gases, but also because both of them are of broad interest as exoplanet biosignature gases. And so we've already heard quite a bit about both already this week. Okay, so in terms of exoplanet life detection, one of our biggest challenges is going to be that in the search for life elsewhere, we are going to be forced to draw conclusions about habitability and even inhabitation based on information that we can get about exoplanet atmospheres. But of course, life on Earth evolved and spent most of its history diversifying within Earth's ocean. And so it'd be highly desirable if we knew how to take information about atmospheres and extrapolate that to infer something about ocean chemistry. So those of you who are familiar with Henry's law might think that this is a relatively straightforward task. And that's because what Henry's law tells us is that the concentration of a gas dissolved in water at the surface of our planet is equal to its partial pressure in the atmosphere times the Henry's law constant. And that constant is specific to each gas, and then it's further influenced by environmental conditions like temperature and salinity. So in other words, atmospheric composition is proportional to ocean composition, or at least in this idealized scenario. And if you have a reasonable estimate of surface temperature, you can place constraints on either atmospheric chemistry or ocean chemistry given the other. And so geochemists apply this kind of logic all the time when we take chemical signals from sediments deposited at the seafloor and try to back out atmospheric chemistry in Earth's history. And it's a sort of assumption that we may be forced to make when we're looking at exoplanets and trying to infer the diversity of surface environments that might exist on those worlds. But unfortunately, it might not be that simple. So to illustrate this point, we can visit Green Lake in New York. Now, at its surface, Green Lake is unremarkable chemically. It's actually quite delightful. But if you peek below the surface, it's really different. Green Lake is actually quite poisonous. And that's because Green Lake totally lacks oxygen and actually has high levels of hydrogen sulfide, which is toxic to us and all animal life on Earth. And so the water in Green Lake isn't blue, and it's not even green. It's actually pink. And that's not from the sulfide itself, but it's from the pigments of the bacteria that are thriving by oxidizing sulfide in the absence of oxygen. So this is light that is widespread in this environment, but it's actually poisoned by oxygen and requires sulfide, despite the high levels of oxygen in our atmosphere and the absence of sulfide, which is quite fortunate for us. I chose to highlight Green Lake because that's a site that I have personally worked at, but an even better example of a oxygen-poor, sulfide-rich environment on Earth today is the Black Sea. The Black Sea is, of course, much larger and has really high levels of sulfide. Again, in extreme chemical disequilibrium with our atmosphere, given the abundance of oxygen and the absence of sulfide. Now, I don't want to give the impression that oxygen deficiency is restricted to special or unique environments on Earth today. This is actually something that occurs in the open ocean as well. So this is a map showing dissolved oxygen concentrations, or the minimum dissolved oxygen concentrations achieved in our ocean today. And so this isn't tied to a specific depth, but instead is a water column integrated minimum. And you can see that oxygen concentrations in our ocean range from roughly air saturated in the light colors to effectively anoxic in the darker blues. And again, this is not tracking spatial variability in oxygen in our atmosphere because we have a lot of oxygen and it's very well mixed. And so these examples aren't meant to challenge the validity of Henry's law, but instead they provide pretty clear evidence that atmospheric chemistry and sea air exchange are not the only factors influencing the chemistry of our oceans and other natural waters at Earth's surface. I mean, in fact, atmospheric chemistry isn't even the most important control on ocean chemistry. And the reason that atmospheric chemistry matters so little is that most of the ocean is actually physically isolated from the atmosphere. So this is a cartoon showing the vertical structure of our ocean. At the top, the yellow sliver is the surface mixed layer. It represents a very small fraction of our ocean, and this is the portion that is actively mixed by the winds, has relatively homogeneous composition, and is actively communicating with the atmosphere. Beneath that, in the light blue, is the pycnocline. That is the region of rapidly increasing density that yields relatively stable density stratification of the ocean and isolates this mixed layer from the deep ocean, which is the bulk of the ocean by volume. This stratification breaks down at high latitudes, of course, in regions of deep water formation. Anyways, the surface layer, the yellow sliver again, is the only portion that achieves chemical equilibrium with respect to sea air exchange, and it does so on a timescale of about a month, which is actually a long time in terms of microbial rates. And so we'll see later in the talk that there is potential even within the mixed layer for biologically induced disequilibrium there. But then the deep ocean goes a long time without actually seeing the atmosphere or knowing what it's made of. So this is now a map showing the ages of deep waters, and they're estimated based on radiocarbon ages. So those ages reflect the time since that water has last interacted with the atmosphere. And you can see that these numbers are actually quite big, particularly in the Pacific, where the ages of deep water can exceed 1,000 years. So again, that's really long timescales biologically. And in this case, the timescales are long enough that the rates of abiotic reactions start to become relevant as well. So this is a long time for the ocean to develop divergent chemistries from what you might expect based on the composition of our atmosphere. So we can say that ocean circulation plays a really critical role in determining the composition of our ocean because it's really the controlling factor on the degree of isolation between the atmosphere and the ocean. Another factor that matters a lot are geologic processes, so things like weathering and hydrothermal activity, which supply ions to the ocean, like ferrous iron and sulfate in particular, that play a really important role in dictating the chemical landscape of the ocean, but ultimately are not in exchange with any volatile phases in the atmosphere. So the role of sulfate in controlling the composition of our ocean is something that I'll return to later in this talk as well. And finally, I've already hinted at this, but microbial metabolism is a really significant and actually the most significant control on the chemistry of our ocean today. And that is likely to be true on other inhabited worlds as well. And so that is going to be the focus of the remainder of this talk. Okay, so here is the outline of the rest of the talk. I've already introduced some of the primary controls on ocean chemistry and highlighted some of the reasons that the ocean might not chemically resemble the atmosphere. But I'll further explore those issues with some examples from Earth's history. And Of course, I will do so with an eye towards the implications for exoplanet characterization. And the take-home message here is going to be that in some circumstances, if not many circumstances actually, exoplanet atmospheres may provide a misleading window to exoplanet oceans and the biospheres living within them. So this is an overview of Earth's oxygenation history. And there are a couple of key things to note here. First is that oxygen rose in our atmosphere in two main pulses. One at the end of the Archean and in the early Paleoproterozoic. We call that event the Great Oxidation event. And we do so despite the fact that the second oxygenation occurring in the Neoproterozoic and early Phanerozoic is actually the much larger oxygenation event in terms of moles of oxygen. So this is on a log scale here and might provide a very misleading view of the relative magnitude of those two events. We saw some oxygen curves yesterday from CUMP in 2008. And the major difference between that curve that you saw yesterday and this curve is that we now think that oxygen levels were probably an order of magnitude or two lower than what that curve depicted. And that's of relevance to this group here because that means whereas we used to think that you could detect atmospheric oxygen on a Proterozoic-like exoplanet, we're now not so sure that that's actually feasible. The other really important aspect of this updated oxygen history is that we now know that oxygenic photosynthesis significantly predates the Great Oxidation event. That's at least by a couple 100 million years, possibly by as much as 500 million years or more. And so the other thing that we have learned since CUMP 2008 is that atmospheric oxygen is not a reliable indicator of oxygenic photosynthesis. And I'm also going to show you that it's not a reliable indicator of aerobic ecosystems and oxygen dependence of the biosphere as well. Okay, so now let's turn to the history of dissolved oxygen. So as we reduce oxygen in our atmosphere down to about 10% of the present atmospheric level, which I'm showing on the left panel, this might be representative of like a late Neoproterozoic, early Phanerozoic Earth. You see that oxygen levels in the ocean decline, as you might expect. In the case on the left, dissolved oxygen concentrations are on the order of 25 micromole per kilogram. Compared to today, there's about 250, 300 micromole per kilogram. So this is about 10% of modern. And you can see that the highest dissolved oxygen concentrations are actually at the highest latitudes where temperatures are lowest and gas solubility is highest. And so the scenario with 10% present atmospheric levels of oxygen actually might map well with your expectations of what the ocean might look like. This is a world that is close to air saturation, or at least within the uppermost layer of the ocean. It's important to emphasize that in this simulation, the entire deep ocean is anoxic. But the surface world could be relatively easily predicted based on atmospheric composition. As you reduce atmospheric oxygen lower, though, to 1 times the present atmospheric level, which I'm showing on the right, in a kind of mid-Proterozoic-like world, dissolved oxygen starts to look really different. First of all, the maximum oxygen concentrations here are about double what you would expect based on equilibrium exchange. And the highest dissolved oxygen concentrations are no longer in the regions of highest oxygen solubility. Instead, the highest oxygen concentrations here are in the regions of the ocean that have the highest nutrient fluxes, thanks to upwelling, and thus the highest rates of oxygenic photosynthesis. And so in this world, oxygen is accumulating where oxygen is being produced, resulting in what we call oxygen oases that are significantly supersaturated with what you compared to what you might expect based on atmospheric composition. And when we reduce atmospheric oxygen even lower, the big surprise is that dissolved oxygen concentrations don't decline further. So on this figure, I'm now showing a huge range of atmospheric oxygen concentrations on the x-axis and globally averaged dissolved oxygen concentrations in the mixed layer on the y-axis. And so that dashed line represents what you would expect for an ocean that was saturated with respect to atmospheric exchange. And the blue line represents the actual globally averaged surface oxygen concentrations. And so for relatively high oxygen concentrations in the atmosphere, the two lines agree pretty well. So for high oxygen levels in the atmosphere, equilibrium with respect to sea air exchange is viable. But as you decrease oxygen lower and lower to Proterozoic levels and even to Archean levels, it's local oxygen production in the ocean that is controlling oxygen concentrations, and they become totally decoupled from atmospheric oxygen levels. And so, be it the Archean or the Proterozoic, we actually think that the surface ocean had on average about one micromole per kilogram oxygen independent of atmospheric levels. And that might sound like very little oxygen, and compared to today it is, but it's actually a biologically significant amount of oxygen. So in the gray shading, I'm highlighting a range of estimates for the oxygen demand of the first animal life on Earth. And you can see that it compares favorably with the oxygen concentrations predicted in our models of the ancient ocean. And so an implication here is that biologically significant oxygen can exist on a large scale in the absence of detectable atmospheric oxygen. And so, of course, those are just model results. I'm not going to get into the details of the rock record in this talk, but when we look for evidence of these environments, we do find it. And the body of evidence for dissolved oxygen in the Precambrian ocean is really diverse, and it's growing. And so it is likely that that these environments did exist on Earth and do exist elsewhere as well. Okay, so the first kind of major take-home message of this talk is that non-detection of atmospheric oxygen on an exoplanet does not preclude dissolved oxygen in the ocean, and it doesn't preclude biospheric oxygen dependence and widespread aerobic ecosystems on that planet's surface. In the case of Earth, we think that oxygen in the ocean predates remotely detectable levels of oxygen by something like 2.5 billion years. So this is not a trivial issue. Okay, now for the second half of my talk, I will move on to methane. And this is a story that really begins in the ocean and involves sulfate. Now, yesterday, Sunny told us about how important it is to consider marine biogeochemistry in refining our estimates of Precambrian methane, and you'll see here that that is actually critically important. So oxygen gets a lot of press because it is the electron acceptor of complex life for energetic reasons. But it's not actually the dominant oxidant at Earth's surface today, that title goes to sulfate. That might sound strange to you, but this is clearly true if you consider that every molecule of sulfate can accept more electrons than each molecule of dioxygen. And its concentration in the ocean is 100 times greater. And so from a strictly electron accounting perspective, the oxidizing capacity of marine sulfate actually exceeds that of oxygen by a factor of 200 or more. And this would be particularly true going back in Earth's history. And of course, sulfate is not an equilibrium exchange with an atmospheric phase. And so viewing Earth remotely, you might end up with a really misleading view of the oxidizing capacity of its ocean. So the history of sulfate in our ocean is not as well constrained as the history of oxygen in our atmosphere. This figure now shows sulfate on the y-axis against time. Note that the time axis is reversed from every other figure that I will show in this talk. You can blame Noah for that. But anyways, we think that sulfate generally increases with increasing atmospheric oxygen, but the details of that relationship are really complex. The oxidation of sulfides during weathering has been complete since the GOEs, since about 2.4 billion years ago. And so what that really means is that the flux of sulfate to the ocean has probably been relatively constant for the last 2.5 billion years. That's not to say that the sink for sulfate in the ocean has been constant, just to say that the sensitivity to oxygen is nonlinear, and we don't fully understand it. But anyways, in the mid-Proterozoic, we think that sulfate was probably less than about a millimolar, or on the order of 1 to 10% present levels. It's certainly low by comparison, but remember that this is still inventory of oxidizing power that rivals that of the modern dissolved oxygen inventory. So this is actually quite important, particularly because it turns out that sulfate is the primary destroyer of methane. The vast majority of methane on Earth today is destroyed by sulfate, not by oxygen, despite its abundance. And this is even more true going back in time. So this figure is showing methane contours in the colored lines against Proterozoic-like atmospheric oxygen levels on the x-axis and Proterozoic-like sulfate levels on the y-axis. You can see that the region of parameter space that allows really high methane levels on the order of 100 parts per million is really small and requires near zero sulfate in the ocean. So now I'd like to overlay some reasonable constraints on the Proterozoic surface environment. So the gray shading kind of shows a broadly inclusive range of parameter space, and the orange shading kind of shows my own bias a bit more strongly. But in either case, you can see that the methane concentrations that are predicted are actually pretty low, between 1 to 10 parts per million if you accept my preferred constraints. So whereas Sunny argued for 10 to 100 parts per million in the Proterozoic atmosphere yesterday, I think that he was probably being quite generous. And so although Sunny and I would agree that as oxygen rose, methane probably declined, I think that if you properly account for life in the ocean, that you find that methane declined much quicker than you would predict based on atmospheric oxygen evolution alone. So of course this has, thank you, biosignature applications. Whereas today, you could confidently detect life on an Earth-like exoplanet using oxygen and its photochemical product ozone. It's not obvious that you could do so at any other point in Earth's history. In the Archean, you might be able to leverage methane as a biosignature, provided that you could find some way to convince yourself that you were looking at biogenic methane instead of geologic methane, which is, of course, a challenge. But the coexistence of methane and CO2 might provide one way to do so. But then in the mid-Proterozoic, when we used to think that this was the best case scenario for remote life detection, because not only could you see oxygen, there wasn't quite enough oxygen to preclude methane buildup, so you could leverage the coexistence of both methane and oxygen and that disequilibrium as an independent biosignature as well. Now, I don't think that you could see either, and it's not because they weren't being produced on Earth, it's because of processes internal to the ocean that allowed them to be cryptically cycled at the Earth's surface without atmospheric expression. So to briefly summarize, the ocean and the atmosphere are intimately linked through sea air gas exchange, but this is not an equilibrium relationship necessarily, in large part because the vast majority of the ocean is isolated from the atmosphere, and because the communication between the two reservoirs is slow compared to biological timescales. And so for those reasons, inferring ocean chemistry from atmospheric chemistry is going to actually be quite challenging. And in some cases, we may have a very misleading view of oceans. And so moving forward, I don't have all of the answers yet, but I think that it'll be really important to try to link our understanding of ocean circulation to observables for exoplanets, because this is something that will strongly modulate the degree to which the deep ocean is communicating with the atmosphere. So that might include understanding things like how planet mass and radius and rotation rate, how surface pressure and temperature affect the mixed layer depth and global upwelling rates. And not only does that affect the efficiency of gas exchange between the deep ocean and the atmosphere, it's also going to affect things like nutrient recycling on a planet, which may in turn actually limit the productivity of biospheres and their detectability. And so I think that this is a great opportunity for models like Rocky 3D, which we've already heard about several times at this conference. And so I would just like to leave you with what I hope is not a controversial statement, and that is that interpreting exoplanet atmospheres is going to require the assistance of oceanographers. And I think that exo-oceanography will play a really important role in our search for life elsewhere. Thank you.
We have time for a couple questions.
That was very interesting. One of the fast timescales that you had in there was the biologic timescale.
Yeah.
And I was wondering, if you had an abiotic ocean, does it become easier and an ocean gets more representative? The atmosphere gets more representative of what's actually in the ocean below?
Yes, possibly, although not necessarily. If the overturning timescales exceed thousands of years, there's still potential for the abiotic reactions to drive divergence with respect to sea air exchange. So things like mineral precipitation or dissolution could be important there. And the role of hydrothermal activity can never be neglected. So on early Earth, we had a lot of ferrous iron in the ocean, and that'll act to remove photochemical oxidants, perhaps from the atmosphere. So yes, but also no.
Okay, one more question.
Your comments about sulfate were really interesting, but is that dependent upon a land surface that is eroding into the ocean? So if you had an aquaplanet, would that change that significantly?
Ooh, yeah, I guess it would. So a lot of the sulfate in Earth's ocean today is the product of chemical weathering of the continents. You could have sulfate that's derived from volcanism on other planets. So I'm not prepared to say that there would be no sulfate in those oceans. You might not accumulate the high millimolar concentrations that we see on Earth, though.